Hello, welcome to the EdSim instruction video called Patient. My name is Nico Punt and I will show you today how you can use the patient object in EdSim++ modeling. Okay, I will drag a patient object onto the screen and I'll double click it to look at its properties, and you can see there are a number of variables. So the patient object contains all the equations and formula to, for instance, use as an input the patient age, body height and body weight, and calculate things like body mass index, body surface area. And it's also capable of calculating the creatinine clearance from a creatinine level. And I will show you this shortly. So let's say that we want to observe the predicted creatinine level, which is calculated in a actual creatinine turnover model, which takes into account creatinine production and creatinine elimination. And I can do a simulation. And you see here a constant line, which is the reference value of creatinine in the blood. It's about 70 micromole per liter. And there we have an actual turnover model in this patient object. I can demonstrate if I attach a output object, and I cannot attach an elimination object, but however I can attach a hemodialysis object. And I connect it here like this. And here I can say, okay, for instance, I have a flow, and I start after 20 hours, and I have a duration of 20 hours. And I have one period. And if I simulate this, you can see that after 20 hours the hemodialysis sets in and actually lowers the creatinine level. So, well, the creatinine clearance remains exactly the same. So this is a purely effect on the creatinine levels by the hemodialysis. Okay, so just a short demonstration that we have an actual creatinine turnover model in this patient object. Okay. Now, what I also will observe is the calculated creatinine clearance, the absolute clearance in milliliters per minute. And so, what this object is doing is it's converting the observed creatinine levels and is calculating a creatinine clearance from this. And there are a lot of options you can set here. Of course, you can set the sex, the gender, the race. And here you can choose the method for calculating the creatinine clearance. So these are the well-known methods like Cockcroft and Gold, the Jelle formulas, MDRD, and the Schwarz-Children formula. Okay, now if I simulate this, and you see here the creatinine level of 70, and here the calculated creatinine clearance, which is about 95 milliliters per minute. Can I have a small look here? Yes, 95 milliliters per minute. Now, if I duplicate the patient object and select a different option here, for instance, the Cockcroft and Gold formula, and I simulate again, so you see still a reference line of 70 micromole per liter creatinine level, and we have here this 95 milliliters per minute using the Jelle formula, and this one is the creatinine clearance calculated using the Cockcroft and Gold formula. Okay, let's remove this one. Okay, what I will do now is I will enter some observations here. I will enter creatinine observations, and I do this by selecting this variable. And let's say that after 10 hours I measure 90, after 40 hours 60 micromole per liter, and after 80 hours 70 micromole per milliliter. The variables, I'm not going to observe the predicted creatinine level, but the interpolated creatinine level. And here is the calculated creatinine clearance. So if I simulate this, I get this pattern. So here are the creatinine levels I observed, and from these creatinine levels I calculate the creatinine clearance. But let's see if we put these values in our creatinine turnover model, how this looks like. And I will do that by also showing the predicted creatinine level. I simulate again. And now we are in for a surprise. So the first level fits. And but here you see, if we calculate the creatinine clearance at this point, the predicted creatinine levels cannot keep up. It won't go through the observed creatinine levels. And on this side it's exactly the same. So there is a discrepancy here. And we have implemented a method in this patient object to solve this problem. And we call this pre-fitting. Now if I go back to the patient object and look at the options, I have here an option that says pre-fit. And if I set it to yes, the following will happen. There will be a correction factor applied to the calculated creatinine clearance, so that the predicted creatinine levels exactly match the observed creatinine levels. And let's see if this works. Yes, you see here, now this correction has been applied, and now the predicted creatinine levels from the creatinine turnover model exactly matches the observed creatinine levels. And I can show you this correction factor that we apply to the creatinine clearance. If I look at variables and I select here the F-core correction factor, which is normally 1. And if I show that as well, and okay, it's a very low value, what I do, I will move it to the opposite axis so that we have a clear view. So here you see the correction factor we applied to the creatinine clearance. So initially, for the first creatinine clearance calculated from the first sample, it's 1. And here the correction is about 1.08, and here the correction is about 0.97. So this is how we can deal with well, dynamic changes in creatinine levels. Okay, I will create a new model now, and I will first add the patient, and of course I want to observe again the predicted creatinine level and a calculated creatinine clearance. I add a hemodialysis, just like the previous model. Oh, must be a hemodialysis. Make the connection. Shift it up a little bit. And we're going to enter a schedule here of 1 liter per hour, starting at 20 hours for a duration of 50 hours. And we have again some observations of creatinine levels. And we have an observation at 10 hours, it's 70. And we have an observation at 35 hours, where it is 60. Now, if I simulate this again, you see that during the dialysis periods, we measured a creatinine level. And this creatinine level is of course lowered by this hemodialysis. But as a consequence, we overestimate here the creatinine clearance. So here also this pre-fitting process can be very handy. So what I will do is I will set under options, I will activate pre-fit again, I run the simulation again, and so what we see is what actually happened. The creatinine clearance did not change at all. So this creatinine level lowering can be completely explained by this hemodialysis. So, thanks to this pre-fitting method, you will be able to correctly interpret the creatinine levels measured during a hemodialysis. So how can we make use of this patient object in ETSIM++ PKPD models? Well, one of the most important applications is the allometric scaling of model parameters. I can demonstrate that using the volume of distribution of a compartment. Okay, I will add a patient object. I will be adding a compartment object. And what I do is I will add observations, and this time not creatinine level observations, but body weight observations. For instance, I have a weight of 80 kilograms after 10 hours, 40 kilograms after 60 kilograms after 40 hours, and after 80 hours it's 70 kilograms. It's of course totally unrealistic, but it's just to prove the principle. Okay, I'm going to say that I want to observe the body weight, and I can do a simulation. You see that the body weight is a so-called interpolated variable. I can make it even more clear if I switch on the X and Y grid lines. Okay, now I switch to my compartment and go to the parameter section. So this is what you know. So we have a volume of distribution as a parameter, and the default value is 1. Now what I can do is I can expose more settings for this parameter by moving the slider to the left. And you can see here that I can set a scalar value, and I will set the scalar value to the patient body weight. So now this parameter, volume of distribution, is scaled by the patient body weight. And I can select here different formats for displaying the variable. I will select this one. So now the variable is not 1 liter. No, its value is 1 liter per 70 kilograms. Okay, now the question, how can I demonstrate to you how the volume is changing during the simulation? And the problem is, of course, that the volume of distribution is a parameter. And a parameter I cannot show in graphs. You cannot output a parameter. But there is an indirect way. If I enter an initial amount in this compartment of exactly 1 milligram, and I'm going to observe the concentration, I am going to show it on the opposite axis. And if I do a simulation now, you see here this body weight, 80, 60 and 70 kilograms. And here you see the concentration. So let's start at the far right. Here the body weight is 70 kilograms. And remember that our volume of distribution was 1 liter per 70 kilograms. So here the concentration is exactly 1. In the moment the body weight is somewhat lower, the volume will also be lower, and the concentration will be higher. And if the body weight is somewhat higher, then the volume will also be higher, so that the concentration will be lower. So in this indirect way we can demonstrate that the volume of distribution actually changes, is scaled with the body weight of the patient. You can also do it in an even different way. So if I switch off the observation of the concentration, I can add a special tool called monitor. And I will connect it to this compartment. And if I now look at the list of externals, I can now enter what symbol must be monitored. I can enter here any symbol. It can be a parameter, a variable, whatever. So I will enter here V for the volume of distribution. And if I go to the variable section, I will then observe the value of this variable. And I will show it on the opposite axis. So I will do the simulation again. And now we see our volume. Here is the body weight. And here you can see how the volume is actually changing. So when the patient is 70 kilograms, it's exactly 1. If he is a bit lighter, then the volume is also less, and if he is somewhat heavier than 70 kilograms, the volume of distribution is also higher. So this is this allometric scaling is very important for more clinical applications, and in fact, it's also used in TDM programs like MW Farm. So this concludes the video about the patient object.